In the last lecture, we were examining unidirectional transport in a cylindrical coordinate system, axisymmetric, so that the temperature field in this case is only a function of the radial coordinate. Okay, so, unidirectional transport. In a cylindrical coordinate system. Okay. And the configuration was as shown. You have a cylinder of radius capital R, okay. A cylinder of radius capital R initially at temperature T1, and at time t is equal to 0, it is instantaneously immersed into a medium with temperature T0, and we would like to know how the temperature decreases as a function of time. Okay. In this particular case, in the long time limit as t goes to infinity, you would expect a steady solution for a cylinder in a medium with temperature T0. That steady solution is just that the temperature is T0 everywhere within the cylinder. Okay. So, that is the final steady solution. So, if I were to consider the cylinder of radius R, okay, and I plot the temperature as a function of radial position. Initially, the temperature is T1 throughout the domain. Okay. So, initially the temperature is T1 throughout the domain, except at the two walls where the temperature is T0. Okay. As time progresses, the temperature will be decreasing with time, okay, until in the long time limit the temperature has equilibrated throughout, it is a constant. And we had defined the scale temperature field as T minus T0 by T1 minus T0, so that the temperature is 0 outside, 1 within the cylinder at initial time, and the steady temperature is just 0. Radius was scaled by the radius of the cylinder, and the time was scaled by alpha t by r square. Okay. So, in terms of the scaled equations, this is the result. Okay. Partial of t star by partial t is equal to 1 by r d by dr of r partial t by partial r. Steady temperature is identically 0 when scaled. Therefore, the temperature field is equal to the transient part. Okay. And we had looked at a solution for the transient part. Okay. So, this is the governing equation. Okay. Expanded out. Okay. This is the governing equation in terms of the transient temperature T star. The boundary condition at r is equal to capital R, the boundary condition is that t is equal to T naught, which corresponds to T star equal to 0. At the center, as I explained in the last class, if you had a temperature that was varying with position, whose gradient was non-zero at the axis, okay, if the temperature was varying such that the gradient is non-zero at the axis, because the system is axisymmetric, as you approach the axis from different directions for an axisymmetric temperature field, the gradient will be along the radial direction. Okay. The gradient will be along the radial direction for an axisymmetric temperature field. Therefore, as you approach the axis, the gradient will approach, okay, different values. Okay. It will be, you will have different values for the gradient at the axis depending on the direction that you approach. Okay. Whichever direction you approach, it is along, the gradient is along that direction alone. Okay. So, therefore, the gradient is not uniquely specified at the origin. You can get a unique value for the gradient at the origin only if the slope is 0. Okay. The other way to think about it is that if the gradient were non-zero at the axis, that means that there is a non-zero heat flux at the axis. Okay. That means there is a non-zero heat flux at the axis. We did see that non-zero heat flux for the case where we had a wire which was emitting heat. Okay. If you have a source at the axis such as an infinitesimal wire that is emitting heat, then the gradient is non-zero at the axis. In this particular case, there is no source. In fact, there is no boundary at the axis. R is equal to 0 is not a physical boundary, it is only a coordinate boundary. Therefore, you require that the gradient be 0 at the axis as shown in this symmetry condition at the origin. And at initial time, the condition is that t is equal to t1 or t star is equal to 1 throughout the domain. Okay. So, we had separated out the equation into two parts, one of which is only a function of r and the other is only a function of t. Okay. Substituted that into the equation, divided throughout by f times g, you get a left side that is only a function of time, a right side that is only a function of r star. When you have one side of the equation only a function of one variable and the other side only a function of another variable, both of which are independent of each other, then each of these has to be equal to a constant, because otherwise you can change time, keep r a constant, and you will find the left side changes while the right side does not change because r has not changed. Therefore, the equality is no longer valid. Equality will be valid at all time and all r only if the left and right sides are constants. That constant has to be negative because you require that for this function g, which is a function of time, this function g has to decrease exponentially as time progresses. Okay. This function g has to decrease exponentially as time progresses, which means that this constant has to be negative. So, we were solving this constant. Okay. I had reduced this equation to an equation of the form of the Bessel equation. Okay. By substituting r plus is equal to beta r star, and the solution that I had got was in the form of Bessel functions. Okay. F is equal to a j naught of beta r plus b y naught of beta r. I had discussed for you the forms of the Bessel function. Okay. The function j naught looks something like this. Okay. That is j naught of x. Okay. And the function y naught, okay, it looks like this. Both of these are functions that are oscillating in time. The time period is not a constant, that is the distance between the zero crossings is not a constant. Okay. Okay. And the amplitude decreases as x increases. Okay. And the amplitude decreases as x increases. Nevertheless, there are multiple zero crossings, in fact an infinite number of those for each of these functions. Okay. Boundary condition at r is equal to 0, the derivative has to be 0. Okay. You can see the blue curve for y naught clearly does not satisfy 0 derivative at the origin, whereas the red curve for j naught does satisfy that. Therefore, in this equation b has to be equal to 0. Okay. B has to be equal to 0 if due to the condition at r is equal to 0, and you get the r dependent term as a j naught of beta r. Okay. The boundary condition at r star is equal to 1 is that this f has to be 0, that means that j naught of beta has to be equal to 0. Okay. J naught of beta is equal to 0 means that the beta is the value at which each of these crosses the origin. Okay. Beta is the value at which each of these crosses the origin. Okay. Beta is the value at which each of these crosses the origin. Okay. Therefore, there is an infinite number of such points at which it crosses the origin. I have given you only the first few points. Okay. The exponential part, of course, in time, okay, beta n square t. Therefore, the final solution is of this form: a n j naught of beta n r times e power minus beta n square t. Okay. And we have to determine this, the coefficients a n from the initial condition. Okay. Okay. at t star is equal to 0. At t star is equal to 0, this exponential part is just 1 and T star is equal to 1, okay, throughout the domain. Note that the temperature was a constant equal to scale temperature was 1 throughout the domain. Therefore, 1 is equal to sigma okay. So, that is the equation, okay, for the coefficients. How do we determine the coefficients? As you recall, for the Cartesian coordinate system, the solution was of the form sine of n pi z. Okay. The solution was of the form sine of n pi z or sine of I pi z. Okay. And the solutions that we got for the coefficients in that case used the orthogonality relation. Okay. Integral 0 to 1 dz star sine of I pi z star sine of j pi z star is equal to 1 by 2 delta I j. Okay. A similar orthogonality relation applies for the Bessel functions as well. Okay. A similar orthogonality relation applies for the Bessel function as well. The orthogonality relation is of the form 0 dr star times r star, okay, or let me, for clarity, let me write this as r star dr star j naught of beta n r star Note that beta n and beta m are values of beta at which the Bessel function passes through 0. Okay. These are the values of beta at which Bessel function passes through 0. Okay. This is equal to 1 by 2 j1 of beta m the whole square, okay, delta nm. Okay. This is also 0 only when n is equal to m. Okay. This is also equal to is also non-zero only when n is equal to m. So, delta nm is 0 if n is not equal to m, and it is non-zero, it is equal to 1 if n is equal to m. Therefore, this is also this integral. Okay. Note that this integral has r star dr star in it. Okay. That is because in a cylindrical coordinate system the area is r dr times d phi. Okay. The area is r dr times d phi. The infinitesimal area in a cylindrical coordinate system, okay, okay, of an interval of thickness dr, the area is r dr times d phi. Okay. So, we have this factor of r here, which was the scale factor that we had discussed when we discussed the spherical coordinate system. Okay. So, therefore, this is the weighting function in this coordinate system r star dr star times the Bessel function, that is equal to half j1 of beta m times delta nm. Okay. So, this orthogonality relation can now be used. Okay. We multiply the left and the right side by multiply the left and the right side by j naught of beta m r star, okay, into 1 integral r star dr star. Okay. And for this integral, I can use the orthogonality relation. Okay. The result I get will be sigma n is equal to 1 to infinity a n This right side is non-zero only when n is equal to m, and I have a summation over n. Okay. So, I can remove the summation and replace n by m. Okay. I can remove the summation and the delta and replace n by m to get the right side as a m j naught of beta m the whole square by 2. Okay. And for the left side you have to do the integral. Okay. For the left side you have to do the integral. Okay. It turns out that if you do the integral r star ds r star j naught of beta m r star into 1, this integral turns out to be j1 of beta m by beta m. Okay. So, that is what you get. Okay, the way to calculate this integral is not obvious here. Okay, so, it is a little complicated, you have to use special functions, but if you do that, finally you will get this as j1 of beta m by beta m. Okay. So, therefore, I get the coefficients a m is equal to 2 by beta m j1 of beta m. And the temperature field becomes T star is equal to summation n is equal to 1 to infinity 2 j naught of beta m r star into e power minus free index here is n. So, I will substitute n here beta n square T star divided by beta n j1 of beta n. So, that is the final solution for the temperature field in this case. Okay. Okay. So, to recall, in this cylindrical coordinate system, okay, as you can see, the differential operator is slightly different. Okay. That is because the surface area changes as the distance changes. Okay. So, the differential operator is slightly different. Okay. And therefore, whereas in a Cartesian coordinate system you get sines and cosines as the solutions, in this coordinate system you get what are called Bessel functions. Okay. These Bessel functions can be plotted by solving the differential equation. Okay. The Bessel function are solutions of this Bessel equation. Okay. The Bessel functions are solutions of this Bessel equation. Okay. For n is equal to 0, the general equation for the Bessel function is this one. Okay. Okay. And for n is equal to 0, it reduces to this, and therefore, the solution we got was in the form of Bessel functions. Okay. So, those Bessel functions also form an orthogonal vector space, okay, an orthogonal function space, in the sense that if you multiply two of these Bessel functions, integral r dr times the product is non-zero only when n is equal to m, okay, and it is 0 when n is not equal to m. Okay. Using that orthogonality relation and the initial condition, which is that the temperature is 1 at T star is equal to 0, right, I was able to multiply the left and the right side by j naught of beta m r and integrate it. The right side, the summation reduced to just one term, because the integral was non-zero only when m is equal to n. Okay. So, using that we were able to find each coefficient in the expansion. Okay. We were able to find each constant in the expansion. There is an infinite number of constants in the expansion. We were able to find each one of them. Okay. So, I should note that in each of these cases we have expanded the temperature field in an what is called a complete and orthogonal function space. Okay. So in the Cartesian coordinate system, this was sine of I pi z, and in the cylindrical this was j naught of beta n r. Okay. And these followed orthogonality relations. Okay. These followed orthogonality relations. Okay. If you multiply two different functions, integrate, you get 0. Okay. This is similar to vectors. So, two vectors are orthogonal when the dot product of those two is equal to 0. Okay. If you have two vectors A dot B is equal to 0, that means that the vectors are both perpendicular to each other and therefore they are orthogonal. Okay. The functions, the vector space, okay, is spanned by these three orthogonal vectors Ex, Ey, Ez. Okay. This. Okay. Such that any vector at any point can be expressed in terms of these basis vectors, and these basis vectors are all orthogonal to each other. Okay. So, Ex dot Ey is equal to 0, Ey dot Ez is equal to 0, Ex dot Ez is equal to 0. Okay. Each of these are orthogonal to each other. Therefore, I have a unique representation of any vector as the sum of a component times Ex plus Ay Ey plus Az Ez. Okay, I have this unique expression because these vectors are orthogonal and they span the space. Okay. In three dimensional space is spanned by three perpendicular vectors. Okay. Similarly, the function space, the space of all functions in the domain 0 to 1 in a Cartesian coordinate system is spanned by these. Okay. And the what is called the inner product, okay, or the equivalent of the dot product for vectors sine I pi z sine j pi z. Okay. This is equal to 1 for I is equal to j and it is equal to 0 for I is not equal to j. Okay. Where this inner product, okay, sine I pi z sine j pi z is defined as integral 0 to 1 dz okay. So, in the same sense that unit vectors in Cartesian space are orthogonal to each other, these functions in this function space consisting of all functions between 0 and 1 in a Cartesian coordinate system, they are all orthogonal to each other. That means that any function can be expressed as a linear combination of these functions, and that is precisely what we did over here, okay, for the Cartesian coordinate system. Okay. For the Cartesian coordinate system, that is precisely what we did. Okay. So, we wrote this as the sum of these functions times the relaxation rate for each of these functions, okay, okay, and then use orthogonality relation to get their coefficients. Okay. Similarly, in a cylindrical coordinate system, this same definition is r dr. Okay, this is equal to half j1 of beta m the whole square delta mn. Okay. So, these functions are also orthogonal to each other. They are 0 if m is not equal to n, and they are non-zero only if m is equal to n. Therefore, in a cylindrical coordinate system, these also form an orthogonal function space. Okay. So, that is the basic, and the total temperature field is expressed as a sum of these basis functions, and each of these basis function has its own relaxation rate. Okay. For a value of beta n, right, the basis function, the time dependence is e power minus beta n square t star. So, each of these has its own relaxation rate. Okay. Okay. So, therefore, you can write these as a sum of these basis functions times a relaxation rate for each of these basis functions. Okay. So, that is the fundamental principle. In cylindrical coordinate system, the Bessel functions are complete and orthogonal function space with the inner product defined as r dr times j naught of beta n r j1 of beta n j naught of beta m r, whereas in Cartesian coordinate system it is just the plane integral. Okay, that is the orthogonal function space. So, basically we are separating out the initial condition into a series of functions, okay, for with eigenvalues with a series of functions either sine of I pi z or j naught of beta I z. Okay. Each of these has its own relaxation rate. So, at any time t you multiply that particular function by its relaxation rate and sum over all of these functions. Any function can be represented as a sum of these functions because these form a complete and orthogonal function space. Okay. So, that is the fundamental principle over here. Okay. T star, okay, is equal to summation of 2 j naught of beta n r star by beta n j1 of beta n e power minus beta n square t star. Okay. N is equal to 1 to infinity. So, there is an infinite series of such terms. Okay. As t becomes large, you can restrict the series at a smaller number of terms because these are all exponentially decreasing functions. Okay. Whereas, when t is small you have to retain all of the terms. Okay. So, initially at initial time, okay, if I plot, okay, r star, okay, r star is 1 is here whereas t versus t star. Okay. Initially if you read, so t star is 1 is over here and you would expect that initially the temperature will be almost a constant and it will decrease sharply near the wall. Okay. Because it is the heat is getting transferred out of this surface, okay, at r star is equal to 1. If you include too small a number of terms, this curve gets smoothed. Okay. So, if I include just one term in the expansion, I will get something like this at initial time. Okay. If I include two terms, I will get something that oscillates. Okay. And it oscillates because this Bessel function here oscillates. Okay. It is because the oscillations in the Bessel function. Okay. So, you need to include a very large number of terms at initial time in order to get the temperature field correct. Okay. As time progresses, if t star is equal to, okay, I think this is t star is equal to 1, t star is equal to 3, and by the time you come to t star is equal to 10, it is somewhere here. In this case, a small number of terms, even one term or 3 terms in the expansion will accurately reproduce this. So, at very early times you need to include a large number of terms in the expansion, okay, because this b e power minus beta n square t star is approximately the same for all the terms. Okay. So, it is different from 1. Okay. Okay. At very small values of t star, this e power minus beta n square t star is approximately equal to 1. As time progresses, these start to become smaller and smaller. So, it is sufficient to keep just one term in the expansion in the late time approximations, whereas at early times you have to retain a very large number of terms. Okay. Okay. So, I will this is as far as cylindrical coordinates are concerned. I will solve one more separation of variables problem, that is in spherical coordinate system, okay, before we go on to oscillatory flows. So, I will continue this in a spherical coordinate system in the next lecture before I go on to oscillatory flows. So, I will continue this in the next lecture. I will see you then.